All right, so let's get started. Welcome everyone to the first Materials Project seminar series. We're really happy to be able to do this. This series is co-organized by the Materials Project and by Materials Virtual Lab. My name is Anubhav Jain. I'm the Deputy Director of Materials Project. Before we get started today, I just wanted to present a few slides about what this series is, and then we'll have our speaker give the presentation. So just to give an overview of this series, so we expect to do this series about monthly. So this will have talks from the top researchers in the field on topics of interest to the Materials Project community. So this could include topics like computational materials design, how to use the Materials Project to perform your research, as well as machine learning applied to materials research. During the talk today, if you have any questions, there's a Q&A button at the bottom of the Zoom panel, so you can ask questions there. Questions will be answered after the talk, so we'll look through the questions and we'll moderate and go through the questions afterwards. Recordings will be cross-posted to a few locations after the talk, so if you want to revisit anything or if you want to share the talk with your colleagues, they'll be posted on materialsproject.org/seminars, as well as the YouTube channel for the Materials Virtual Lab. If you like the series, if you think that you would make a great speaker, or you know someone that would make a great speaker, we are definitely accepting nominations for speakers. So see the initial email that you got about the seminar series, and you'll see a link to the nomination form, or contact me and we can send you that link. All right, so before getting to today's speaker, I just wanted to mention our upcoming seminars. We have one on August 18th with Zach Luisi, professor at Carnegie Mellon, and we also have one in September with Sinead Griffin, who's a staff scientist at Berkeley Lab. So we hope you'll be able to join us for those seminars as well. Today, kicking off the Materials Project seminar series, we have Jakoah Brgoch, who is an associate professor at University of Houston. He has done wonderful things about finding new materials through a combination of theory and experiments and machine learning using Materials Project tools, as well as other things that's been developed in this group. So I'm sure you'll hear all about that today. We're excited to kick this off. And Jakoah, why don't you go and take it away from here?
All right. Thank you very much for the introduction, Anubhav, and thank you for the invitation and the opportunity to present some of our research that we're carrying out here at the University of Houston that we've been doing for the past 6 or so years. Over the last 18 months or so, it's been really challenging for everyone. But I do have to say that I know everyone's getting tired of Zoom meetings and Zoom conferences, and they're certainly not as good as the real thing. But one thing that I have noticed is the fact that learning that we can get together and meet at least virtually and talk about science and share ideas is something that has certainly propelled my research forward in many new ways that I would have never thought about. So I do hope that, even though things are not far from ideal, that maybe we can at least keep some of these benefits and as we move forward. So today I'll tell you specifically about one of the projects that's been going on in my group here at U of H, and that's using machine learning and computation to target new superhard materials. I'd like to first start by thanking the students who do the work that you'll hear about today. This project most recently has been spearheaded by a really talented graduate student in my group,
Jakoah, I think your slides aren't showing right now, so.
Oh, let's see. Are they? I wonder if they. Let's see. I think they stopped sharing when you were sharing, maybe.
Yep.
I think we
got it back now. There
okay,
we go.
Cool. Yep. Thanks. So I'll just like to thank the students who did the work that you'll hear about today. So the work was really most recently been driven forward by Ziyan Zheng, who's an extremely talented graduate student in my group. The project was kicked off, though, by a now former graduate student in my group, Arya Mansouri Tehrani. Arya has since moved on to a postdoctoral position at ETH in Zurich, working with Nicholas Spalding. Arya worked very closely with a former postdoc in my group, Anton Olenyk, who has started his independent career at Manhattan College in New York City. And Arya and Anton did a lot of the initial machine learning and synthesis work that you'll hear about in my talk. They both worked very closely with Zeshan Rizvi, who's a former undergraduate in my group, and then most recently, Jakoah has also started on this project. I've been fortunate to receive a variety of different funding support for this project. The project was initially seeded by American Chemical Society Petroleum research funding, and then it was carried on with some support by the NSF. I also have support from the National Institutes of Health as well as the Welch Foundation, which is a really great resource supporting fundamental chemical research here in the state of Texas. I'm also a principal investigator at the Texas Center for Superconductivity, and I was awarded a 2020 Sloan Research Fellowship in chemistry. So I'd like to first take a little bit of a step back and kind of introduce the way that my group addresses questions in inorganic, let me see. Oh, there we go. Addresses questions in inorganic chemistry, because we do so from a fairly unique perspective. And that's the fact that my group does both computation and machine learning, as well as material synthesis and characterization. And we really try to intertwine both of these as much as possible in every single research project that we do. What does that mean? Well, let's take the example of a new student who wants to join my group and they're interested in materials synthesis and characterization. I'll design a new project for these students to come in and learn how to carry out inorganic solid state synthesis and crystallography, physical property measurements. But at some point, I'll put these students in front of a computer and I'll teach them how to run first principles calculations or maybe do some data science work. I'll show them how absolutely easy it has become today to run some of these computational codes like VASP, but I'll also show them how challenging it is to interpret the results correctly and draw something meaningful out of these computational outputs. The opposite is true as well. I'll have students who come to my group and want to do computation, they want to do machine learning. And so I'll put together a data-driven or computational-based project where they can go and predict crystal structures or physical properties. But at some point, I'll push these students into lab and I will teach them how absolutely challenging it is to make some of these materials that they can calculate. Harder yet is to make some of these materials phase pure and understand crystal structures and the crystal chemistry. And so by going and doing these projects in sort of a hybrid approach, we really cross traditional boundaries. And I think by doing so, I have training and I train my students in a way that allows them to really think of innovative ways to address some really big challenges in inorganic materials chemistry. So we apply this hybrid approach in a number of different research fields. The one that you'll hear about today is using machine learning to target new superhard materials. We also have a project where we're using data-driven search and computational work to identify novel metal-rich solids. You know, a lot of the high throughput computational work has been made possible by the fact that, you know, there are tens of thousands, if not hundreds of thousands of crystal structures contained in inorganic crystal structured databases, for example, that have been, collected and put together over the last 50 and 60 years worth of research. So our work is looking at how do we accelerate the identification of simply new materials? How do we build these databases with unknown compounds faster? Now, the largest area in my group, though, is the development of luminescent materials for application in things like LED lighting or display technologies. We also have a pretty interesting project where we take these same luminescent compounds called phosphors and we make them as nanoparticles and we put them in what's called a lateral flow assay. This would be probably most commonly recognized as the home pregnancy test. And because these are luminescent nanoparticles that we are putting into these tests, we're pairing the test with a cell phone flash and a cell phone camera. And what we can do with these tests is that after you run the test, you take the cell phone flash and you irradiate the test strip, and then you can use the camera to take a picture and determine whether or not the test is luminescing or not. And by doing it in some specific ways, we're able to get a 10-time improvement in sensitivity compared to some of the state-of-the-art over-the-counter tests available today. This work on these nanodiagnostics has been done in very close collaboration with some of my colleagues in chemical engineering here. And in fact, a few of the students have gone on and created a startup company called Luminescent that's now in the Bay Area, doing extremely well. In fact, they're the 8th FDA emergency use authorized COVID test for point of care diagnostics. So they're doing very cool things. This is a space I definitely think is worth paying attention to. But as I said today, I'll tell you about our work in targeting new super hard materials. And the reason why we're interested in super hard materials is because I would argue that these are some of the most underappreciated inorganic compounds in existence today in terms of their application. Super hard materials touch virtually every aspect of modern daily life, from the clothes on your back to the technology that I'm speaking to you through right now. These are the types of materials that go into things like drill bits that are used to access all sorts of new ore deposits and bring materials to the surface that can then be refined and go into the computer chips that we're using on our laptops. I'm also in the state of Texas, and so naturally I have to have a project in oil and gas, and all of these types of high hardness, super hard materials are used in drill bits for accessing petroleum reserves. You know, over the last 18 months, I think a lot of people have found that they like to try and at least be do-it-yourselfers at home and have to make a lot of trips to Home Depot. And a lot of these materials go into things like cutting and grinding tools like skill saw blades. And no one wants to have to make more than one trip to Home Depot. So if you were to ever have a skill saw blade that would last a lot longer, that would be definitely ideal. There's a lot of applications for super hard materials that maybe a lot of people wouldn't even think about. Things like artificial joint replacements. You know, if you have to have a joint replacement early enough, or rather early in life, you know, these artificial joints still need to have be fairly wear resistant, because over time, you know, an artificial joint replacement is going to last on the order of maybe 5 to 15 years, depending on how much sort of natural wear there is. And so if we can think about replacing specific parts like the femoral head in terms of the artificial joint replacement with a wear-resistant, high-hardness material, these types of joints are going to last significantly longer. This is a pretty large market. The market for super hard materials is projected to surpass $14 billion by 2024. More impressive yet, though, is that Wood Mackenzie, which is an oil and gas consulting firm based out of Houston, estimates that there's going to be a needed $1.7 trillion investment by mining companies to support the clean energy transition. You know, if we want to start thinking about you know, something like an all-electric future where batteries become you know, more and more important, or photovoltaics, we're going to need to access the mineral deposits, things like lithium and cobalt that go into batteries, for example. And, you know, Wood Mackenzie even took into account the fact that there's going to be an increase in terms of the ability to recycle materials, but they still found that a $1.7 trillion investment will be needed. And a significant portion of that is certainly going to go into super hard materials that make up, again, things like drill bits and grinding tools. Now, when I'm talking about super hard materials, you can really kind of classify the state of the art into two different groups of compounds. The first are going to be compounds that you're probably the most familiar with. These are going to be materials that contain only light elements like boron, carbon, nitrogen, something like synthetic diamond or the classic cubic boron nitride, maybe this BC2N. There's also more exotic phases like this boron 6 oxide. Now, the synthesis of super hard materials is possible in sort of an industrial setting, but they require extremely high pressures, 15 gigapascals, more than 2100 degrees Celsius. And the really big issue here is the fact that the pressure and temperature of 15 gigapascals and 2100 degrees Celsius needs to be applied concurrently. This is effectively a bomb that you need to make these high pressure phases. And these are not easy synthetic conditions, but you know, as I said, industry has found ways. You can go to the store and you can buy things out of synthetic diamond or buy materials based on cubic boron nitride. And so there's a significant enough market that industry is willing to invest in the safety approaches, but it's not without cost, and that drives up the cost of these materials in general. Now, the field of super hard research was really turned upside down a number of years ago when Rick Kainer's group at UCLA showed that competitive materials with things like cubic boron nitride could be achieved when you take a transition metal and mix it with a main group element like boron, nitrogen, or carbon. This would be typified by compositions like rhenium diboride or tungsten tetraboride. The excitement of these phases stems from the fact that the synthesis of these borides only requires elevated temperatures, like 1500 or 2000 degrees Celsius. Now, my colleagues in organic chemistry tend to, laugh when I talk about doing synthesis at 1500 degrees Celsius. This is just a ridiculous temperature for organic chemistry. But from a materials chemistry perspective, 1500, 2000 degrees Celsius is really all not that crazy. In fact, we've been able to achieve these temperatures for hundreds, if not thousands of years, right? 2000 degrees Celsius is just a standard metallurgical temperature, which we know how to reliably and safely access. The fact that you don't need the combination of high pressure and high temperature for the second class of material is really what has driven the interest in this second group of compounds. Now, looking at the physical properties, if we plot just the first type of compound here, like diamond, cubic boron nitride, I'm plotting the material's Vickers hardness. And so just to make sure that we're all on the same page, hardness is just a materials property where we're talking about the resistance to indentation. And so if you take any sort of surface and you kind of polish it to a mere shine, and then you take an indenter tip and push on the surface, it's the amount of force or the resistance to the indentation. Now, the indenter tip can have a variety of different shapes. And so within our research, we focus on Vickers indentation. This is one of the most common. So Vickers is just the shape of the indenter tip. And so we're looking at Vickers hardness value. And you can see things like diamond have Vickers hardnesses ranging from 70 to 90 gigapascals. Cubic boron nitride is lower, 45 or so to 60 gigapascals. These compounds all fall above this 40 gigapascal superhard threshold. So anything above 40 gigapascals is considered to be superhard. Now, the hardness of these phases arises from the fact that you have short directional covalent bonds by these main group elements. Take, for example, diamond. You have these sp3 hybridized orbitals that point perfectly at other sp3 hybridized orbitals, and they form these very strong short covalent interactions. And that's what gives rise to the high hardness in something like diamond. Now, if we look at the second type of high hardness material, what you can see is that their hardness is a little bit lower. Something like rhenium diboride is 30 to 55 or so gigapascals. Tungsten tetraboride is a little bit lower. Osmium diboride is lower yet. Now, the hardness of the second type of material stems from the fact you have a combination of 4D and 5D transition metals with a really high electron density, a high bulk modulus. If we're talking about a resistance to indentation, it turns out that there's actually nothing harder than having to push a valence electron into the core, right? The repulsive forces are just too high. And so taking and combining this high valence electron density with the short covalent bonds stemming from the boron, the carbon, the nitrogen, is in fact why we get these, really impressive mechanical properties. But as I said, with the first class of super hard materials, one of their big limiting factors is the fact that you need a really high pressures and really high temperatures in order to synthesize the compounds. Well, the second class of compounds, as you can see, contain elements like rhenium and tungsten and osmium, right? These are extremely scarce and exceedingly expensive elements. So if we want to start talking about, $14 billion worth of super hard materials, the synthesis of that much super hard material is going to be just an outlandish cost where industry is not even going to consider these types of compounds. And the other issue that stems from the fact of these second class of materials is the fact that there's sort of an anomalous issue with hardness. And that's the fact that hardness as a materials property is not a single value. Most materials, if you were to ever talk about hardness, they don't just have a single hardness value. It turns out that hardness has a range of hardnesses that stem from different applied forces. So as I said, you take and you push on a surface and the hardness is how much resistance there is to indentation. But depending on how hard you push on the surface, the hardness can be different. So if you have a higher applied force, the hardness tends to be lower than if you have a low applied force. And you can see that this is sort of an intrinsic response of all materials. All materials have some sort of range where you have high applied load and low applied load. Now, the origin of this load response is really not all that well understood. People just sort of lump it together in what they call the indentation size effect, but nevertheless, this is something that you're going to have to contend with. And what you'll notice is because of this indentation size effect, things like rhenium boride at high apply load fall below the superhard threshold, and things at low apply load fall above the superhard threshold. So they sit right around the 40 gigapascal line. Well, of course, as you can imagine, people who spend their careers investigating the first type of super hard material, where they clearly fall above 40 gigapascals, really hate the fact that people investigating the second group of material also call their compounds super hard. And in fact, the people that investigate the first type of super hard material have actually created a new threshold sitting at 80 gigapascals that they call ultra hard material. So if it falls above 80 gigapascals, it's now ultra hard. Well, whether it's ultra hard or super hard, these are both just sort of arbitrary cutoffs. Nonetheless, there's still some controversy about whether these materials are in fact super hard or not. So within my group, we thought there was some opportunities here because I have a strong interest since my PhD in the chemistry of borides on the whole. So I thought that perhaps there was some opportunity here that we could go and look at developing new transition metal borides that are not going to fall at the superhard threshold, but hopefully fall above in this region in our sort of uncontroversial in terms of their super hardness. And then also maybe we can identify compounds that are no longer containing these expensive elements. So as with every one of our projects, because we do both experiment and computation, anytime we start a new research project, we always see if we can approach it first from a computational standpoint. But one of the biggest challenges in terms of doing hardness as a research project is that we very quickly realized that starting a project on hardness from a computational standpoint was going to be extremely difficult. And the reason is shown very clearly, I think, in this molecular dynamics simulation. So here is in blue is a copper block that contains a few 10,000 atoms and an indenter tip. And what we're going to do within this molecular dynamics simulation is simply indent the copper block. And what you can see is the copper block is indented. The blue, these are residual forces. The blue forces or residual forces start to become, green and red. These are going to be high amounts of residual forces. You can see that the process of indentation is not even captured in this multi-thousand atom molecular dynamics simulation. With periodic boundary conditions, this is just not an ideal setup. My group's expertise is in density functional theory, and the fact that we can't even capture the process of hardness using molecular dynamics tells us that density functional theory is not going to be necessarily reasonable in terms of modeling the material's resistance to indentation. And then there's other issues that we also have to consider, and that's the fact that when we're indenting a surface, it's not like we have a shovel and we're just like scooping the atoms away off of the surface. If you look at these AFM images, what you can see from the indentation is that the atoms have to go somewhere as you push on the surface. And as the atoms move out of the way, they undergo significant amounts of what's called pileup, or, maybe would be closely related to things like surface reconstruction. And what you'll see with this surface reconstruction is that even in the molecular dynamics simulation, this is not well captured. And so, we can't cover the length scales necessary with DFT, and we certainly can't cover the surface reconstructions necessary at the DFT level. And so if we want to think about designing new super hard materials, we are initially a bit concerned, thinking that we maybe didn't have really any opportunities here. But as we did a little bit digging deeper into the literature, we did start to come across some opportunities that we thought might be worth pursuing. And that's the fact that a number of different research papers have shown that materials' intrinsic properties, things like the bulk modulus, have been directly correlated to a material's Vickers hardness. So as you can see here, plotting the bulk modulus, so resistance to compression against the Vickers hardness, has somewhat of a relationship. It's not ideal, but there's definitely some linearity here. If you plot a material's shear modulus, that's going to be resistance to lateral strain across the crystal structure. You can see that there is, in fact, a better relationship. It sort of starts to fall apart at really high Vickers hardnesses and high shear moduli. Nonetheless, there's a fairly nice linear relationship here. This work has shown, though, that the best relationship is achieved when you plot a material's G cubed over B squared. So this is a G divided by B is better known as Pugh's ratio. And so this is like a shear modulus weighted Pugh's ratio. And you can see that plotting G cubed over B squared, you get a really nice relationship over all of the hardnesses probed. And so where we were really sort of intrigued is the fact that, bulk modulus and shear modulus are both intrinsic materials properties. And better yet, you can actually calculate bulk modulus and shear modulus using first principles calculations. So fortunately for us, right around this time is when we when the materials project started making their first push of elastic tensors. So you need the elastic tensors in order to get a materials bulk and shear modulus. And so we started to take a look a little bit closer at using things like elastic tensors to do some large scale material screening of for materials that might have really high hardness. But one of the things that we sort of, again, kind of quickly realized is that, despite all of the really great work, and this is, I would say outdated, but this is when sort of our first project started in October of 2018. They had, just over 7,500 elastic tensors. This is now beyond 14,000 elastic tensors. Even then, this is still only a fraction of the number of band structures that have to be calculated or that have been calculated. In order to calculate the elastic tensors, you have to use density functional perturbation theory. And this is, computationally a pretty big task. So doing high throughput calculations, although possible, is expensive. And even then, if we start thinking about the number of compounds that have been calculated, this is still less than 5% of the known inorganic crystal structure databases. So the ability to go through and calculate these at the first principles level is, again, it's a good opportunity, but it's not ideal. And as we thought about it further, there's other challenges, of course, with doing pure DFT screening. Things like the inability to account for site sharing. You can do this with DFT, but it's not super straightforward, and it's not very straightforward in a high throughput format. There's also challenges dealing with highly correlated electronic systems. Again, it's possible with DFT, but it's not ideal, especially in a high throughput format. Now, because we're also interested in hardness, there are some things that are not even addressable with DFT. Again, hardness crosses multiple length scales. The idea of using DFT would be amazing, but the fact that we have to not only look at local chemical interactions, but also interactions between different grain structures is going to be a huge challenge. And then finally, there's no ability that I'm aware of to calculate a load dependence of hardness using DFT. And so, we knew that there was something here. We were really excited by the fact that we had access to now so many elastic tensors provided by the Materials Project data set. And so we wanted to think maybe a little bit about how we could use this data to at least guide our search for super hard materials. And so what we turned to was the fact that maybe we couldn't use the DFT calculations directly, but instead maybe we could shift towards doing machine learning. And all of this sort of pioneering work in machine learning and materials science, and this huge transition that everyone has been making has been really made possible by the fact that every machine learning project needs a large data set. And things like the Materials Project and the other high throughput computational databases have finally provided access to a well-curated, really large data set. And so database development is always the sort of the slowest part of any one of these research projects. And so what we did was we went in and we pulled the Materials Project elastic tensors and calculated the bulk and shear moduli for all of the compounds. But as with any machine learning project, one of the first things that you want to do is go through and do data sanitizing. You want to make sure that the data that you're putting into your model is reliable, because your model is only going to be as good as your input data. Now, I'm sure that the team on the Materials Project side do a lot of data curation before they ever put out new compounds. But one of the things that we have found is that, to be honest, there are still times when materials or rather data come through that just don't make sense. For example, especially early on, there were a number of elastic tensors that would have negative elastic moduli, for example, which make no physical sense. We want to make sure that we remove these from the training data set. The other thing that we do, though, within my group that's a little bit more rigorous is the fact that, and it's definitely worth pointing this out, is that things like the Inorganic Crystal Structure Database and Pearson's crystal data set, these contain hypothetical compounds. Compounds or crystal structures that have been predicted using things like genetic algorithm prediction approaches. Now, as you can imagine, within my group, who are doing both experiment and theory together, at the end of this project, our ultimate goal is to identify a new compound that we can synthesize. And so one of the things that we do within my group is that we always sanitize the input data set against only experimentally known compounds. And so we went through and we removed all of the hypothetical compositions, and we're left only with experimentally confirmed compounds. So when all was said and done, we were left with 2,572 bulk and shear modulus, including binaries, ternaries, and quaternary compositions. So that's our input data set. Now, the next step in any machine learning project is going to be data representation, creating a feature set or a descriptor set, it means the same thing, in order to describe the input chemical compounds to the computer. Now, every research group that does machine learning has sort of their own flavor or flair of descriptor set. Within my group, we use a combination of composition variables as well as structure variables, things like atomic number, atomic weight. We also use things like space group number and crystal system. In terms of composition, the way we describe a compound as a descriptor is we use the variable or numerical operations, things like largest, smallest, average, difference. Let's just take, for example, cubic boron nitride. The way that we represent cubic boron nitride, let's just say it by atomic number. The atomic number of boron is 5, and the atomic number of nitrogen is 7. So we input, 5, the number 5, the number 7. We input 5 plus 7, 5 minus 7, or the average of 5 and 7, and this is just the way that we put in the data. And then in terms of the crystal system, for example, we would tell the model that it's cubic or give it space group number 225, for example. And so by putting in the data in terms of these 150 descriptors, we're now able to clearly and reliably represent our input bulk and shear moduli. So the next step that we want to do, though, is we want to, now that we have a large data representation and data set, is see if we can interpret our features and see sort of what features matter overall. And so what we did was we did some informatics types approaches related to things like principal least squares analysis, and we calculated what's known as the variable importance projection score, or a VIP score. And in this case, you can see for the bulk and shear modulus, the bigger the bar, the more important this is going to be related to that specific material's property. Now, if we look at all 150 descriptors, you can see there's really not so much that stands out. And so what we did was we went and we decided that we would reduce the number of features using a genetic algorithm feature reduction. And that's shown here. You can see that when all was said and done, we were left with 71 important features or essential features for the bulk modulus and 55 features for the shear modulus. And when we do this feature reduction, you can see the VIP score becomes a lot more telling. One of the things that you'll notice right off the bat is, for example, things like cohesive energy matter for both bulk and shear modulus. Something like metallic valence matters. On the crystal structure side, other things stand out very clearly. Things like density matter for both bulk and shear modulus. There are other surprising things, though, that come out. For example, electron density matters for bulk modulus, but this valence electron density matters for shear modulus. Now, it's not always clear why maybe valence electron density matters for one, but electron density matters for the other. We don't always necessarily understand these things. But you can also separate this out and say things like, crystal class and inversion center don't matter. Now, the benefit of doing this is that, ultimately our goal is to do some materials design. We want to identify, what sort of chemical compounds might give rise to really impressive bulk or shear modulus values. And so this type of information gives us sort of the crystal chemical handles that we can, use to sort of tune the material's properties one way or the other. If we want to drive up a material's bulk modulus, we know we're going to need to influence things like the cohesive energy or the density or the electron density. And we know by, turning up the electron density, that's going to influence positively our bulk modulus. If we try and change our crystal class, that tells us that doesn't really matter. And so this really provides sort of some nice insight that helps us guide our understanding of these types of materials. But this is just sort of from an informatics approach. This isn't really any machine learning. Now, in terms of the actual machine learning, we take our data collection and our data representation, and now we can do some model construction. Again, every research group sort of has their own focus or expertise in terms of model construction. You can do things like random forest or neural networks. Within this project, we tested a lot of different models, but what we found was that support vector machine tended to work quite well based on the data set size and the properties that we were trying to predict. So I'd just like to give you a little bit of a quick primer in terms of support vector machine. So support vector machine was originally designed as a classification algorithm. So that's going to be essentially separating the gray from the orange. And what you do is you essentially want to identify a hyperplane that allows you to determine whether a new unknown data point falls on the gray side or the orange side. And so you can clearly see that this line is able to linearly separate gray from orange with high accuracy. But it's not necessarily just that line that you could have drawn. You could have drawn any one of these lines, and all of them separate out gray from orange with high reliability. What support vector machine does then is it identifies the line that finds the optimal hyperplane that maximizes the margin from the support vector. So all of these data points shown here are called support vectors. And support vector machine finds the line with the slope that maximizes the distance from all of the support vectors. Now, why would it do that? Well, let's just take a step back. Let's say that you chose this slope right here. You like the shallowest slope line, and your next unknown data point falls right where my laser pointer is sitting. You can see that your next unknown data point would be on the orange side of the line, so you would classify this unknown compound as orange. But if you were to actually go through and maximize your margin, you would find, in fact, that my laser pointer is effectively now sitting on the gray side of the line. So in fact, without using support vector machine, you would have had a misclassification. So doing something like support vector machine is really just a fancy way to minimize your error. But this is a pretty straightforward example here, and it's of course not always that straightforward. So the true power of something like support vector machine is that it's not always easy to see how you can linearly separate gray from orange. And in support vector machine, what you can actually do is perform what's sort of known in the field as the kernel trick. What you can do is you can take and undergo a numerical substitution. You can take a data set that looks something like this, and you can undergo a mathematical substitution using a variety of different kernel substitutions. And you can ultimately separate out your data in higher dimensional space in order to then maximize the margin and find the optimal hyperplane. And so that would be the example of taking something like a function that would be 2x squared and take x squared and replace it with some more complex function of z, and then you can linearly separate your data in this way. In our case, if you're technically interested, we use a Gaussian radial basis function for the kernel, and then we use tenfold cross-validation for all of our model. But this is a classification example, right? We're separating gray from orange. What we're trying to do here is we're trying to do a regression. We want to put in a material's bulk modulus or shear modulus and then predict the bulk and the shear modulus. And so you can effectively do the same thing, but rather than undergo the linear separation of gray from orange, here we can just undergo a linear regression and minimize the error in W and B and find a new function in high dimensional space that allows us to quantitatively predict the material's bulk or shear modulus. And so that's what we did. We took the 2,572 binary, ternary, and quaternary compounds from the materials project, and we trained the model using our reduced feature set. Here you can see here's the bulk modulus coming from the materials project. Here's our cross-validated bulk modulus using support vector regression. You can see across the entire data range probed that we get a really reliable model. The dark regions are where we have a significant amount of data overlapping. If you look at our histogram, you can see that nearly all of the compounds fall within 10% error, or even better than that. So overall, we get really reliable prediction. Our R squared, cross-validated R squared is 0.94. Our root mean squared error is 17 gigapascals. So this is pretty reliable. Now, the shear modulus is not quite as good. You can see that the shear modulus statistics, the R squared is only about 0.84. Root mean squared error, though, is about 16 gigapascals. This is still reasonably good. But if you look at the parity plot, you can see it's not ideal. You can see that we have significant more scatter. The shear modulus data tend to be clustered a lot lower, between 0 and about 200. You get some really high shear modulus, shear moduli up here. But in fact, above 200 gigapascals, you're starting to talk about really sparse data. And so that's probably why we get significant underestimation at really high shear moduli values. You can see that that's reflected in the histogram here, not really that reliable of a prediction overall. Nevertheless, at the time when we published this work, this was, in terms of bulk and shear modulus, competitive with, everything that was out there in terms of the literature. And then honestly, it's still competitive with a majority of the new models that are out there today. So we were pretty comfortable with our prediction for bulk modulus and our prediction for shear modulus. And so what we did was we now went back to the Pearson's crystal data set, and we extracted the compounds of 118,000 compounds, including 15,000 binaries, 56,000 ternaries, and 46,000 quaternaries. And once you train the model, which really does not take all that long, because support vector machine is really efficient even in terms of training, we're able to predict both bulk and shear modulus in less than 30 seconds for even more than 118,000 compounds. And we're not using any high performance computing clusters here. This is just on a normal desktop. So this is pretty impressive to take the 2,572 input data and scale this really reliably out to 118,000 compounds. Now, if we take the 118,000 compounds and we plot the bulk versus the shear modulus, here you can see sort of what the data look like. You get a significant amount of data overlap here in the center in the darker region. It's worth pointing out that we have 27,698 compositions containing rare earth elements. We have just under 20,000 compounds with disordered or mixed positions. These are not generally accessible using high throughput calculations, and yet here we are able to access them pretty reliably. But now the question becomes, if we want to look for new super hard materials, where do we do that? Where do we look out of these 118,000 compounds for new super hard materials? Well, fortunately, as we were working on this project, Rick's group put out a really nice review that sort of took a holistic look at the field of super hard materials, thinking about this idea of super hard materials design. And what they noticed very intriguingly was the fact that all super hard materials are also ultra incompressible, meaning that they have a bulk modulus above 300 gigapascals, but the reverse is not necessarily valid. Let's take, for example, elemental osmium. Okay, if you think about just elemental osmium, you can see the bulk modulus is very, very high, but the hardness is very low. Well, osmium is a metal, and its bonding is going to be related to the sort of sea of electrons that we teach our general chemistry undergraduate students. So from an indentation standpoint, what that means is that if we have two sort of just think metal spheres of osmium atoms, is we're going to indent the surface. The bonds holding the osmium atoms together are not necessarily all that strong. And so osmium can the atoms themselves can sort of rearrange however you want. And the bonds and the distribution of the electrons are going to, again, remain sort of in this delocalized sea picture. But if you take something like boron and you add in, these covalent bonded elements from the main group, what you begin to do is you sort of add in a scaffold that's going to hold the osmium atoms in place. So now if the osmium metallic atoms want to start moving around, they can still move around somewhat, but they start to bump into these covalently bonded scaffolds that are not going to move. In the field, this would be related to what's known as the resistance to dislocation motion. You're essentially preventing dislocation or the movement of atoms. Now, there's no easy way to measure dislocation motion, at least at the first principles level, but there is a relationship between dislocation motion and shear modulus. Think back to my introduction slides, right? Shear modulus was related to hardness nearly linearly, and that's going to be related to the material's dislocation motion. Now, there's no clean cutoff for shear modulus and dislocation motion, but sort of an analysis of the different types of high hardness materials suggests that, you know, anything above about 150 gigapascals for the shear modulus should be okay. And so what we can do now is take this plot of 118,287 compounds. We can put our bulk modulus, ultra incompressible cutoff line here, and we can put our dislocation motion shear resistance at 150 gigapascals here. And we know that any new super hard materials are likely to fall in this region in the top right corner. Okay, we can take a look a little bit closer at the compounds contained in this top right corner, and what do we see? Well, we see exactly what we would have hoped. Compounds like cubic boron nitride fall right here in the top right corner. Well, this should not be that much of a surprise that boron nitride is its own impressive island, because boron nitride is really the only compound that's competitive with synthetic diamond. It's worth noting that on our screening here, we only have binaries and higher. We don't have any elemental compounds, so diamond's not present here. But boron nitride has been around an industry standard material for the better part of 60 or 70 years. So it's not a surprise that it has, was sort of discovered without needing anything like machine learning or computational development. It is simply just the best material available. You'll also see that other compounds sort of falling within the larger cluster are also in the region that we would have thought. Things like tungsten carbide or tantalum carbide, compounds that you can go to Home Depot and buy drill bits that are made out of today. There's also this tungsten tetraboride, which is currently being commercialized by a company in the LA area called Supermetallics. They're developing abrasives made out of this tungsten tetraboride. So what this confirms to us is that, hey, we're at least looking in the right region for new super hard materials. So what we wanted to do now was see if we could pick one of these unknown data points, one of the just gray data points here, and see if we could synthesize it and in fact confirm our predictions. So, I didn't want my students to go into lab and synthesize anything like a simple binary. So we selected this, slightly more complex pseudo-quaternary phase, molybdenum tungsten borocarbide, that we thought was really interesting. Now, here's the cool part about the work that we do in my group is that Arya and Anton went through and they made all of these predictions. They trained the machine learning model. They did all of the data analysis in my student office, and then they headed across the hall and they went into our synthetic inorganic chemistry laboratory, and they actually made this compound. So you can make molybdenum tungsten borocarbide by starting from just the elemental powders. So you take the powders and you just sort of can mix them together so they're nice and homogeneous, press them into a pellet. We then use arc melting to melt these elements. So arc melting is basically you just take a jar and purge all oxygen out, backfill it with argon, and then you strike an electric current through the argon, which creates an argon plasma. You can really easily achieve temperatures at 2,500 to 3,000 degrees Celsius quickly. You melt all of the elements together and you end up with an ingot that looks like this, a really nice, shiny, well-faceted product. Breaking this apart and doing electron microscopy shows that we have uniform distribution of the tungsten and molybdenum atoms. Collecting powder X-ray diffraction shows that we're able to make a really nice phase pure product. There's a little bit of graphite impurity. You can barely just see it right here below 2. Graphite's really inert even at 3,000 degrees Celsius. And so getting it to react can be somewhat of a challenge, but we were able to optimize our synthesis with a bit of effort to make this product. Looking at the crystal structure, you can see that it's orthorhombic. It's actually pseudo-tetragonal. But one thing that's really sort of an oddity about this crystal structure is the fact that A is about 3 angstroms, C is 3 angstroms, but B is this really long length. It's 17 angstroms. So it's a super anisotropic crystal structure. Well, this was a bit of a surprise because if you go back to any of the older literature that describes sort of how would you design super hard materials from an empirical standpoint, one of the rules that they would have always suggested or emphasized is that it has to be a cubic crystal structure. Again, think diamond, cubic boron nitride. This is definitely not cubic. But if we look at the crystal chemistry of that a little bit closer, one of the things that you'll see is that molybdenum boride and tungsten carbide make up the crystal structure. So we're able to have an idea that this is in fact going to be related to these types of compounds.
Professor Brgoch, it looks like we have just a couple more minutes for the presentation, then we can move on to the questions if possible.
Sure, yeah, I'll finish up here just a couple seconds.
Perfect.
So what we did was we went ahead and measured the materials bulk modulus. We wanted to make sure that our machine learning predictions were in fact correct. So we went and did high pressure diamond anvil measurements. So in this case, you grind up the powder, put it between the diamonds and compress the unit cell. You can fit the refined volume of the unit cell to a Birch-Mernigan third order equation of state. Here by diffraction, you can see our bulk modulus 370 gigapascals. Support vector regression predicted 373, and DFT on an ordered supercell model is 353. So overall, excellent agreement. Looking at the materials Vickers hardness, well, this is exactly what we had hoped. So you can see that at low load, we are sitting right at the 40 gigapascal superhard threshold. As you increase the material, the load applied to the material, you can see the hardness decreases. Again, this is the load, the indentation response curve. It bottoms out around 26 gigapascals, so this is still quite good. We were really happy with the fact that this is sitting around 40 gigapascals, at least at a half a Newton. So where does this compare with respect to these other compounds? Well, molybdenum tungsten borocarbide is better than osmium diboride. We're competitive with tungsten tetraboride, which, as I mentioned, is being commercialized. We still fall below these types of compounds, but it's worth highlighting the fact that this is a compound that had not been studied before, and we picked it out of our sorting diagram. More importantly yet is the fact that it contains molybdenum, which is definitely not as expensive as rhenium or osmium. But one of the things that you might notice is that our goal was to identify a super hard material that falls entirely above the 40 gigapascal threshold, and we didn't quite make it there. And the reason for this, as I mentioned, we're sort of using an indirect proxy for hardness. This is not really giving us any idea of how do we predict the material's hardness still. So where we took this project next was the fact that we wanted to see if maybe we could just use machine learning to directly predict a material's Vickers hardness. And as I said, any machine learning project needs to have an input training data set. So what we did was we went back to the literature and we started to extract data from the peer review literature. We also added our own hardness measurements that we carry out in the lab as our training data. And we were able to put together just over 1,000 Vickers hardness data and the associated chemical information and applied load. Looking at the data distribution here, you can see that our Vickers hardness training set covers 57 elements on the periodic table, largely made up of early transition metals and main group elements. We don't contain things like alkali metals or halogens, but this should make some sense because there's really no structural materials that are based on alkali halides. So there's really just no interest in measuring these types of materials. Our data distribution, you can see here, is quite imbalanced. Most of the compounds, almost 90%, fall below 40 gigapascals, but we do have some high hardness compounds. Our load distribution is again mostly at a half a Newton, but there's some data at higher hardness, higher applied load as well. Now, we tried to use things like support vector machine and random forest for training the model, but what we settled on because of the data imbalance was using gradient boosting, particularly extreme gradient boosting. That seems to work the best in this case. Overall, our model is really outstanding. Our R squared is 0.97. The mean average error is 1.7 gigapascals. Particularly the mean average error is notable because the experimental measurements on hardness are generally about 10% error. So overall, across the entire range, we're doing really well. As I mentioned, we always want to validate our model. And within my group, we tend to only trust experimental validation. We go always beyond statistical confirmation of a model's trustworthiness. So in this case, what we used was we turned towards using transition metal disilicides that had never been measured for their experimental hardness. So we looked at these compounds because you get a range of crystal chemistries and a whole range of different transition metals that can be used. Here you can see that we're able to synthesize all these as phase pure products based on their fine X-ray diffractograms. Measuring the experimental hardness, you can see here's the hardness measured. Here's our extreme gradient boosting prediction. Overall, really good reliability at a half a Newton. Gets a little bit worse at 5 Newton, but remember we have less data at 5 Newton than a half a Newton. Where we were really excited is the fact that if we plot the load response curve, so here you can see apply higher load, hardness drops, we're able to capture this almost perfectly with the XGB model for all of these different compounds here. Here I'm showing 3, but all 8 show reasonable reliability. It's worth pointing out, though, that these are only up to a hardness of about 26 gigapascals. We're interested in super hard materials. Okay, so here, looking at something like cubic boron nitride, you can see almost quantitative agreement between our model and cubic boron nitride. It's worth pointing out that these are all held out, so these are not seen by the model, the prediction set. We're able to just nearly predict rhenium diboride with a little bit of underestimation, and we're quantitatively predicting tungsten tetraboride. So we're confident in our ability to now predict super hard materials, including the load response curve. And in fact, as far as we're aware, this is the first time that this has been demonstrated. So what does that mean for our previously discovered compound? Well, here was the experimental measurement, and here is our Vickers hardness prediction using XGBoost. Right, you can see nearly quantitative agreement, just a little bit of an underestimation. More importantly, we're able to identify the fact that here's what our load response curve looks like. So what we could have arguably done if we would have had this model to begin with is go through and predict the material's Vickers hardness and determine whether or not at low load and high load we were going to be falling within the super hard regime. So with that, I'd just like to conclude by saying that the development of new superhard materials is definitely going to be possible in phases that contain transition metals and main group elements. I think there's a lot of phase space left to cover, and a lot of research needs to be done. Machine learning is going to be play a huge role in the ability to screen these types of compounds, particularly because something like DFT is not really a tractable problem, and molecular dynamics, although there's been a lot of really cool work in terms of on-the-fly machine learning potential development, is going to be limited, particularly in terms of the more complex crystal structures. I think borocarbides are a really interesting class of compounds. They're understood or examined for things like high temperature materials, but not so much for high hardness materials. But finally, I think the key in not just for super hard materials discovery, but material science in general, is having access to high quality training data, either in the form of computational outputs or even in user generated data sets. It's going to be vital for pushing data driven material science forward. And the work by the crew at the Materials Project and all of the other high throughput approaches have been really a huge benefit to the community, and their work is really only going to just keep pushing the field forward. So with that, I'd like to thank everyone for joining my talk here today, and I'm happy to take any questions.
Perfect. So thank you so much, Professor Brgoch, for the wonderful talk. We've had lots of questions pouring in during the course of the talk. We may spend the next 5 or 10 minutes going through some of these.
Yeah.
If we don't get a chance to go through all of them, I'll put a link in the chat where people can continue the discussion on one of our forums. One question that people had was about crystalline versus amorphous materials for hardness. So the question was, what does your experience tell you regarding additional opportunities for the discovery of superhard materials that are amorphous, and is crystallinity a prerequisite for superhard materials?
Yeah, that's actually partly one of the ways that the field, in terms of what I kind of talked about with the ultra hard materials, that's the way the people doing these diamond type materials have gone. So that's where there is certainly a huge amount of opportunity in terms of taking something like diamond and then distributing nanocrystalline participants of diamond within the matrix, because there you start to sort of artificially introduce or limit dislocation motion. Now, this is, I think, coming a little bit more from a materials science perspective, right? Controlling participant distribution is at that point. We're looking at it from a standpoint of how do we simply identify these new materials. But then the people are absolutely right? You can then take the hardness and you can only drive it higher. A little bit like the field of thermoelectrics, just to make a comparison, right? You can find a material with the new high ZT, but then you start play these sort of multi-scale games where you can do things to enhance the properties further, and that's the way it'll be done here. Similarly, I see there's some comments about thin films. That's where the advantages of thin films certainly have over bulk materials. Now, my background and strength are in bulk materials, and you have a much harder time doing things like controlling nano precipitation in a bulk material at 3,000 degrees Celsius. Growing thin films is really where the benefit is gonna lie there. So yeah, I think that's a great question, and if we want to talk about really driving hardness up, that's where the field is sitting in these sort of hetero structures, if you will.
Great. We had another question about temperature. So it asked,
Yeah.
are all the data sets temperature project at 0K? And what about the effective temperature on hardness, et cetera?
Yeah, that's a cool question. So it's a really cool question because we actually just put out a paper that was accepted today in JPhysChem Let. So keep an eye out on that. And that's looking at how does temperature affect hardness. And hardness is temperature is detrimental to hardness. So something like diamond, you actually have other issues with diamond, and that's the fact it starts to sublime above about 500 Celsius. So if you put it in an atmosphere, yeah, the hardness of diamond drops by something like 50% at about 1,000 Celsius. So what we did within the paper that we published in, will be coming out in JPhysChem Let, is actually go through and build on our data set and incorporate temperature as an external parameter, just like we did for applied load. And what we showed in this case is that you can also predict the temperature dependent hardness as a function of load as well. So you kind of get the external parameters in there. Now, how do we mitigate or minimize temperature dependent hardness? That's a bigger question. I don't really have an answer for that one yet. I'm not really sure, because that's a good one. I mean, that's exactly where we would like to go, is think about what can we do to change the chemical bonding so that we're minimizing or mitigating the effects of temperature. We now know how to predict the materials. Now we have to think about how to minimize that. So that's a really cool question. But check that one out. That'll be, I don't know, however long. Like I said, it was fortunately accepted today, so I can say that. So it'll be out there as an ASAP or whatever JPhysChem Let does soon.
Awesome, great news. Yeah. Another question is thinking more broadly. This question asks, if we're able to synthesize the material after making it by ML, why isn't it in industry yet? So, preferably over the less harder materials. So, what barriers still stand in the way after ML synthesis? What's next?
Yeah, it's yeah, it's one of those things. Like, scalable synthesis is a different beast. And we haven't really investigated it that much in terms of our super hard materials. But let me just jump back a couple slides here. So like the ingot here that we have made is 200 milligrams, right? So this is 200 milligrams of product. And I don't know about you, but if you want to talk about industrial synthesis, 200 milligrams is not exactly going to take you very far. But this is what people are working on. So the company Supermetallics is actually a spinoff out of Rick Kainer's group, and so that's what they're looking at. How do you take and maintain temperatures of 2,000 degrees Celsius to sinter these types of compounds? And that's a little bit outside my expertise. But the main hiccup here for sure has been elemental cost, right? So it's something like tungsten is reasonable. That's why they're commercializing tungsten tetraboride. Rhenium diboride has better properties. It's a non-starter, right? So it's always a balance of how can you scalably make a material at a cost where your company's not going to be, just losing money on starting material. So I hope that kind of answers the question. But there are techniques, right? There's all sorts of high pressure, high temperature furnaces that can be done. Even arc melting. I mean, we've just bought a new arc melting furnace that will allow us to scale up and go to a few gram synthesis. But that's still far from, I'm sure, the metric tons that will be needed or that are produced of these materials.
Great, thanks. We had a set of related questions about the feature generation and also the feature reduction of the machine learning. So for the feature generation, the question was, how transferable are these handcrafted features to for your problem, and how well do they scale to other problems? And then the feature reduction parts is, can you just talk a little bit more about it? And are there like multiple correlated properties where your machine learning model is randomly picking one over the other? So any more details about that process, I think, would help address some of these.
Cool. Yeah. So the features are super transferable, and I think that's what everyone, that's why I say sort of every group kind of has their own flavor. I mean, we do the work on data-driven luminescent materials development, and we use sort of a base set of similar features, and we always sort of curate them from there. So for example, within this project, what's an example of a good one is somewhere in here is going to be, yeah, right here, number 19, Gilman's valence electron density. So one of the pioneers in the field of super hard materials was a guy named John Gilman. And he's since passed away, but he's written a number of books on, well, papers and books on super hard material design. And at one point, just sort of randomly, he put this valence electron count for super hard materials for all of the elements. And you know, we pulled this information to put it in as a descriptor set. And somewhat interestingly, you'll see it doesn't really have that much influence on the bulk and shear modulus, but we also did the same feature reduction for our Vickers hardness. And what we actually see is that it matters for Vickers hardness. So we do go through and build or curate our training or our descriptor set for each individual project. But by and large, you know, this is probably one of the most transferable ones, and it's probably really similar to things that are going to be out there in things like you know, PyMat, or not PyMatGen, in MagPy and AutoMap Miner, right? I'm sure Anabov probably recognizes a lot of these features, right? These are sort of the common core ones that go into most machine learning models. Yeah, and then there's other ones, you know, sort of the question about, you know, what stands out, what doesn't, you know, especially if you look at structural, you know, it doesn't surprise me that something like inversion center doesn't matter with respect to a hardness. Where we were surprised is something like space group number doesn't really seem to matter, right? Everything tells us that cubic crystal structure should be the best, and then we go through and we see this, and it's like, oh, well, maybe not so much. But then there's other ones that you know, clearly make a lot of sense. Density and volume per atom. You know, these are things that if you were to go through and read John Gilman's old books, I mean, he did this from an empirical analysis. He didn't have, you know, any fancy informatics algorithms. He simply took a step back and thought through the problem from a chemical standpoint and was able to identify a lot of these relationships. So almost everything that we identified here, for better or worse, was honestly known. I mean, these are things that if we would have spent, you know, spent the effort to read through all these books, we could have come up with a lot of these rules as well. But it's also super cool to think, hey, we can go through and confirm all of this stuff from a truly large data standpoint.
Great. Maybe one last question. So this question asks, is high melting point one of the criteria for super hard materials? This might be the formal definition as well as, you know, practical implementation. What do you think of melting temperature as a criteria as well?
Yeah, so this is one that we've always thought about sort of from a multi-materials property application standpoint. And there, you would think that there's a relationship, and there really is not so much. I mean, there's definitely I would say a positive correlation, but there's not a direct relationship. One of the things that I've always found a little bit interesting is I've always really wanted to use you know, machine learning to predict melting point of materials. But it doesn't work, and I don't really know why. I've never seen it in the literature. I think a lot of it is probably because if you start thinking about getting materials melting point, particularly in the solid state realm where we're talking about these borides, there are not many people in the world that can measure you know, melting points passing 2,000 and 3,000 Celsius, right? It is a challenging measurement. You'll notice that I actually didn't even talk about confirming the shear modulus from our prediction. Shear modulus on its own is a very challenging measurement to do. You have to do things like ultrasonic spectroscopy, things like that, or resonant ultrasound spectroscopy. They're just not that straightforward. So I think part of the limitation in melting point is going to be just the fact that you don't have that much data, and anything that you have is going to be fairly skewed. So it's almost like an inverse data set here. We don't have any information on lithium halide, or sorry, alkyl halides, but I am sure there's a lot of melting point data on alkyl halides because you can do it at reasonable temperatures using just a standard TGA. So there's got to be a relationship. I'm sure it's not a direct one-to-one correlation. High hardness does not necessarily mean high melting point, but there is going to be a connection, right? Carbides are some of the highest melting point materials, and a lot of carbides are some of the hardest materials, but they're not necessarily super hard. So a direct or you know, a relationship, but not a direct one-to-one correlation.
Okay, perfect. So with that, I think we'll end for today. Thank you everybody for joining. As Dr. Brgoch said, during these times where it's difficult to meet in person, we're really happy that you were all able to join us and ask these wonderful questions and be able to listen to the seminar. We hope you'll join for next month's seminar as well as future seminars as well. And remember, future discussions further discussions on this talk will still continue at materialsproject.org/seminars. So we hope to see you there, and we will see you again next time. Thanks, everybody. Bye-bye.